Hi everyone, this is chapter 6. We are going to solve the cost minimization problem for firms. Here is the overview of today's presentation. We will first distinguish what is meant by long run and what is meant by short run. We will then define the ISO cost lines, which are graphically similar to the budget line that we have seen in consumer theory. With the distinction of long run and short run, we will first solve the long run cost minimization problem, and we will specifically discuss how we solve for 3 different types of production functions. I will also present them both graphically and mathematically, and I will also make a comparison between what we did uh, in the consumer theory. We will then talk about the comparative statics, which is what happens if the input prices changes, and what happens if the output changes. Lastly, we will solve the short-run cost minimization problem, which is, well, we will see what that means. The terms long run and short run sound like they are referring to the length of time period, but absolutely how long is considered as long run? There is not a definitive answer. And essentially, those two terms are referring to the degree of flexibility that the firm has in making its decisions. We think that long run is the period of time that is long enough for the firm to freely choose the quantities of all of its inputs, while in the short run, the firm is constrained and is not able to choose at least one of its inputs. This might be because of previous decisions. For example, the firm has decided to build a plant, and it is not easy to, say, sell the plant or to rent the plant to someone else in a short period of time. It may also be that the firm wants to purchase new machines, but those machines do not arrive like the packages we order on Amazon. That's in a few days. But those new machines have to be manufactured by other firms and may take years to be delivered. So based on this, different firms actually have different definitions for the long run and the short run. For example, if we think of a tech firm that hires software engineers to develop programs, then to expand its capital, which are mostly computers or high performance servers, well, those can be ordered and delivered in possibly weeks or maybe a few months at most. However, if we think of an airline company that want to purchase new aircraft from the Boeing company, it may take 1 year or 2 years or even more than that for the new aircraft to be delivered. In this case, the airline companies are not as easy as the software companies when they want to make adjustment to the amount of capital they are using. And lastly, if we look at the right picture, I'm not exactly sure what that machine does, but you can imagine if whichever firm using this machine wants to purchase or construct a new one, it's going to take quite a long time for that to happen. And they cannot as easily make adjustment on this aspect. And those are more realistic examples, but in our case, we want to focus on the simplified model of it. So we think that as we have been focusing on 2 inputs, labor and capital, we think that in the long run, the firm can choose freely all of its inputs, and in our case, labor and capital. While in the short run, the firm is constrained in at least one of the inputs it uses. And we think that capital is less easy to adjust in the short run as compared to labor. So we would say that in the short run, the amount of capital the firm can use is fixed. We can extend our model a little bit and say if we have a firm using 3 inputs, labor, capital, and land, then in the long run, the firm can choose all of them. And in what's called median run, the amount of land is fixed, while the firm can increase or decrease the amount of capital and labor it employs. It is less easy to purchase or sell land. And in the short run, both the land and capital are fixed, and the firm can only choose labor. And while this is a slightly more complicated model than one we are going to be focusing on, and we are not going to cover this in this course, but we can imagine that I'm adding medium run here, but in reality, the firm does not simply face long run or short run or medium run, but the firm faces a continuum of runs. And the concept of this long run and short run only is essentially saying how flexible the firm can adjust its inputs. And we are going to use this distinction later on when we start to solve the cost minimization problem. Before we do that, we want to define another concept, which is the ISO cost lines or the ISO cost curves. So this is analogous to the budget line we see in the consumer theory. So this ISO cost line is a set of combination of labor and capital that will incur the same cost for the firm. So we have been assuming that the firm uses two inputs, labor and capital. So let's suppose there is a price for those two. And let's say the wage is $10 per hour per labor hour, and the rent for capital is $20 per machine hour. Then we can write our ISO cost line as TC equals to 10 times L plus 20 times K, right? So 10 times L is the total amount of cost the firm would have to pay for labor if the firm hires L units of labor. And 20 times K is the total cost the firm has to pay for capital if the firm hires K units of capital. And then the sum of those two is the total cost of the firm. So for any L and K, such that 10L plus 20K gives us the same value, which means those combinations of labor and capital are going to incur the same amount of cost for the firm. We say that they are on the same ISO cost line. And more generally, we write the total cost equals to W times L, the wage rate, times the amount of labor hours the firm uses, plus R times K, the capital rent rate, times the amount of machine hours the firm uses. So I'm writing it down here, but I will show this in the next slide. This ISO cost line has a slope that equals to the negative of W divided by R, and the intercepts on the axis are the TC divided by W and the TC divided by R respectively. So let's draw a graph of this for the given wage rate and the capital rent rate. We have labor on the horizontal axis, and we have our capital on the vertical axis. So let's see, what if TC, we want to draw a total cost curve that TC equals to 100. So an ISO cost line, where the firm pays $100 as total cost. This is basically 100 equals to 10L plus 20K. So we are going to draw a line that is represented by this expression or this equation. And we've done this a few times, and I'm going to do this again. So if L equals to 0, you can find that K equals to 5. I should have put if over here. If K equals to 0, L equals to 10. These are the two intercepts that we can find on the axis. And to draw this, let's say this is L equals to 10, and this point is K equals to 5. So this iso-cos line will be a straight line connecting these 2 points. And this straight line is the iso-cos line for TC equals to 100. Now, if we want, we can draw a different one, that is TC equals to 200, for example. Then that is basically drawing 200 equals to 10L plus 20K, right? And to figure out those intercepts, if L equals to 0, we have K equals to 10. And if K equals to 0, we have L equals to 20. So for this second iso-cos curve, let's say this is L equals to 20, and this point is K equals to 10. Then the iso-cos curve, the second one, is a straight line connecting these 2 points. So this is TC equals to 200. All right, and we can, let me just draw a third one real quick. So let's say we draw a third one, that is TC equals to 300. And I'm going to skip some steps. I know that if L equals to 0, K equals to 15, and if K equals to 0, L equals to 30. So for this third iso-cos line, it is going to intersect this point and this point, and we can connect it. That's probably something like this. So this is our third iso-cos line. And we can draw infinitely many of them as much as we like. All of them are going to be parallel to each other because they have the same slope. So for, let's see. So for a general total iso-cos line, that is TC equals to W times L plus R times K. Let's see what's its slope. So we can rewrite this expression. We can write this. We can write K as a function of L. So we move the W times L to the left, and we divide both sides by R. So it will be TC divided by R minus W divided by R times L equals to K. Or let me put K on the left. So K equals to TC divided by R minus W times R, minus W divided by R times L. So from this expression, we can see that our slope is the coefficient in front of L, which is negative W divided by R. So the slope is negative W times R, and the intercept on the vertical axis is TC divided by R. And this is how we have been finding the intercepts, right? So we are basically setting our L equals to 0 when we were finding the intercept on the vertical axis. And to find the intercept on the horizontal axis, we are setting our K equals to 0. So the intercept on the horizontal axis is TC divided by W, which is found by setting K equals to 0. This is found by setting L equals to 0. And I've written this on the previous slide as well. And let me just emphasize this here again. The slope is negative W by R, and we have the W equals to 10 and R equals to 20. So the slope is negative 10 divided by 20. That is negative half. And it's the same for all those three isocost lines. Because when we draw different isocost lines, we are changing the level of total cost from 100 to 200 to 300. But we are looking at the same wage rate and the capital rent rate. So the slopes for all the isocost lines are the same. All right. So after defining the isocost line, we are ready to first define the long-run cost minimization problem, and later on we will solve it. So let's suppose the firm's production function is given and it's fixed by some function, and the firm wants to produce a Q0, and we call the Q0 the target level of output. I probably should have put here. Q0 is the target level of output. It's just a name. You don't have to remember this or anything. And we will figure out in chapter 9 why the firm will choose or what Q0 will the firm choose. It will be a result of the profit maximization problem for the firm. So now we are solving the cost minimization problem, which is telling us that if the firm were to produce Q0 units of output, what is the most efficient way of doing so, or what is the way, or what combination of inputs will incur the lowest amount of cost for the firm? After answering this question, then we can look at, well, if the price of the output of the firm are sold in the market at some level, then which Q0 should the firm choose to maximize its profit? And well, we will solve that in chapter 9. But for now, let's just say the Q0 is some exogenously given value. And we are answering this question, what combination of inputs is going to incur the smallest amount of total cost for the firm if the firm were to produce Q0 units of output. And to define this problem mathematically, somewhat similar to what we did in consumer theory, we are going to minimize the total cost, and the two variables that is below the minimize sign, L, K, is saying that the firm is free to choose labor and capital. And the total cost equals to W times L plus R times K. So the firm is choosing L and K such that it minimizes W times L plus R times K. And the firm has a constraint, or the firm has a target. So it is subject to the constraint that the output it produces must be Q0 units. All right, so the production function F, L, K, this production function must produce Q0 units of output. So the firm must choose L and K such that it produces Q0 units of output, and also that it minimizes the total cost for the firm. We have an intuition for this cost minimization problem. So we know that the firm has different levels of isoquants, right? And each isoquant represents the combination of inputs that will produce a certain level of output. So now the firm is constrained and must produce at least Q0 units of output. So I probably should have added here that the firm is looking for an input combination that is on isoquant, and specifically on isoquant that Q equals to Q0. And we will see what this meant in the graph in the next slide. And the firm also want to minimize cost. So it would want to also find an input combination that is on the leftmost possible isocost lines. Because the more to the right, the ISO cost lines, the higher the total cost the firm is going to incur. And if you remember in the ISO cost graph we draw just now, when we have TC equals to 100, it is to the leftmost. When we increase TC to 200, it shifts to the right. And when we increase TC to the 300, it shifts to the further right. All right, so the leftmost ISO cost line is going to incur the lowest amount of total cost. So here I want to show you how we do this on a graph for Cobb-Douglas type of projection function, and I want to make a comparison between the utility maximization we did in the consumer theory. So let me first draw something, and let me divide our screen into two. So on the left, I'm going to do the utility maximization problem for a Cobb-Douglas utility function. And on the right, I'm going to do a cost minimization problem. And I want to make a comparison between those two. So in the utility maximization problem, the consumer has a budget line that is fixed. And I'm using the red color to represent something that is fixed or something that is the target, all right? And the consumer has a different bunch, different kinds of indifference curves. So there are many of them. And this is U equals to U1. We have U equals to U2. That is larger than U1. We have U equals to U3. That is larger than U2. Because the higher the indifference curve, the higher the level of utility. And we have this, our budget line. And we find the point where our budget line is tangent to our indifference curve to find the optimal consumption bundle, right? That's what we did in the consumer theory. Now, in the projection theory or the cost minimization problem of the firms, things are look almost the same, but there is an important difference or an important distinction. So we have a isoquant that is Q equals to Q null, let's say, that is fixed. And we have a whole bunch of ISO cost lines that we can draw for some given ratio of the wage rate and the prices. So the blue ones are the ISO cost lines. So this is TC equals to TC1. This is TC equals to TC2. That is going to be larger than TC1. And on the rightmost, it is the ISO cost line represented by TC equals to TC3. And because it is on the right, we know that TC3 is going to be even larger than TC2. So the important difference is that the red line, let me write this in black. The red line is the fixed. The red curve, I would say, is the fixed target. And in the utility maximization problem, it is the budget line that is fixed. And the consumer is trying to shifting the indifference curves and find the one that is highest possible and also that also still intersects the budget line. In the cost minimization problem, however, it is the isoquant that is fixed. The firm must produce this much output. And we are shifting our total cost curve, which are the straight lines, and we are finding the one that is to the most left possible, which will represent the lowest level of total cost, and that still touches our isoquant. This will be the one that is minimizing the firm's cost. So we are looking for a blue line, a blue curve, or I would say, that is, well, highest in consumer theory, and in the producer theory or the cost minimization problem, it is lowest in the producer theory. So although they would look almost the same, but what is fixed and what is changing or what is moving is different. So I think it's okay to put it here. And we already derived the condition for the consumer theory. For the producer theory, it is going to be very similar. So we can see that the cost minimization input combination happens at this tangency point, right? So if we call this point A. So the condition for finding point A is that the slope of our ISO cost line is the same as the slope of our isoquant. Because only when they are tangent will this point A minimizes our total cost. And we explained why this is the case graphically in consumer theory already. And we are going to also combine this with the fact that A must be on the isoquant. So point A must produce the target level of output that is 2, 0. And also at point A, the slope of the ISO cost line must be the same as the slope of the isoquant. So this is how we can find the cost minimizing input combinations. So let me see if I have covered everything I want to say in this slide. Okay, so the important distinction I want to make is essentially here. So what's different is what is fixed and what is changing. are different in the two cases, all right? So this is, I think, the most important difference between the two cases. Moving to the mathematical expressions, we are going to see that everything will look quite familiar. So if we have a general Cobb-Douglas production function, and as we discussed, to find the cost minimizing input combinations, we are going to employ the tangency condition. That is, the slope of the isocost line is the same as the slope of the isoquant. We derived previously that the slope of the isocost line is negative W divided by R. And we knew that the slope of the isoquant we derived in previous lecture. It is the marginal rate of technical substitution, and that equals to the negative ratio of the MPL divided by MPK. So the tangency condition is eventually going to be W divided by R equals to MPL divided by MPK. We can use this part, and we are going to use this equation to find the corresponding optimal ratio of labor and capital. I probably should have put it here. The optimal ratio of the labor and capital. And we are going to combine this optimal ratio with the other condition that the firm must produce the target level of output. And we can solve for the cost minimizing input combinations. And we will do a numerical example later on. Now let's move to the cost minimization problem for perfect substitute. So for perfect substitute, everything is really simple. And I'm going to continue to use the color red to represent what is fixed, and to use the color blue to represent what is moving, all right? So for perfect substitute, the isoquant are straight lines that we know. So this is our isoquant, Q equals to Q0. And we also have isocost curves. And it really depends on which one is steeper. So let's suppose the isocost curves are steeper than our isoquant. That means the isocost curves look something like this. Okay, let me adjust the graph a little bit. So let me adjust our isoquant so that it is not as flat, which will make my drawing easier. All right. So here we have 4 different isocost lines, and Q equals to Q0 is the isoquant or the target level of output the firm must produce. So basically the firm must choose a point that is on the red line. So let me label the axis, as we always should have done at the beginning. And we can probably tell that which point will the firm choose. So, well, it's probably going to be one of the endpoints. So if the firm chooses this point, that is point A, or do the firm choose this point, that is point B? Well, we can see that the 4 total cost lines, TC1, TC2, TC3, and the last one, TC4. And because TC1 is to the left, TC1 is going to be smaller than TC2, which is going to be smaller than TC3 and TC4. We have this ordering of the total cost, right? So this implies that the total cost of using input combination A is going to be smaller than the total cost using input combination B. So point A minimizes total cost. And we can probably see and argue that no point on this red line, the isoquant is going to possibly incur a lower level of total cost than point A does, because TC2 is the leftmost isocost line that we can shift. So here we are choosing point A because our isocost lines are steeper than our isoquant. So because isocost lines are steeper than our isoquant, we use all capital and no labor. So what does this corresponding to? So when isocost lines are steeper than isoquant, it means that the absolute value of the slope of the isocost lines are larger than the absolute value of the slope of the isoquant, right? So this is going to mean that W divided by R is larger than MPL divided by MPK. This implies this equation. And we know that we are going to use all capital and no labor in this case. So similarly, if the isocost lines are flatter than the isoquant, then this corresponds to the case when the slope of it is smaller than the slope of the isoquant. We know that in this case, we are going to use all labor and no capital. And lastly, it is a rather special case when the isocost lines have the same slope as the isoquant. That corresponds to the case where W divided by R is the same as MPL divided by MPK. Then any point on the isoquant is going to incur the same total cost for the firm. And all of them are going to be basically the same. And let's call this case 1. Let's call this case 2. And call this case 3. So the graph we draw over here is actually case 1, right? This graph that we see is case 1. So what happens when it is case 3? That's a little special, and let me draw it here. And we have our isoquant that is fixed and always represented by the red line. This is our isoquant. Now, if the slope of the isocost lines are the same as that of the isoquant, then when we draw the isocost, they are going to be parallel to our isoquant. So we have these isocost lines. And most importantly, there is one isocost line that is perfectly fits what the isoquant looks like. So every point on the isoquant are going to be on the same isocost curve. And if this is our TC3, so every point on the isoquant is going to incur a cost that is TC3 for the firm, and every point is basically going to be the same for the firm, and all of those points are cost minimizing points. The firm has no incentive to choose a point that is higher than TC3, and the firm is not able to choose a point that is lower than TC3. This case is a little special, and we actually tested a question under consumer theory in the midterm exam. I think it's a true and false question. So let me see if I missed anything for this slide. Okay, I think it's good. All right. So to summarize, when we have perfect substitute, we are going to make a comparison between those two expressions. And here I rearranged the expressions a little bit. I rearranged so that we are comparing the MPL divided by W and MPK divided by R. And this has a similar interpretation as what we had in the consumer theory. So we can imagine that the MPL divided by W is the marginal product of the last dollar spent on employing labor. And the MPK divided by R is the marginal product of the last dollar spent employing capital. Now, if it is always the case that the marginal product of spending an additional, if it is always the case that the marginal product of spending an additional dollar on employing labor is higher than the marginal product of spending an additional dollar on capital, then the firm will only use labor. And conversely, if capital is more productive marginally than labor, the firm will use only capital. And eventually, when they are the same, then it doesn't make a difference as to how many capital and labor the firm uses. And recall that the production function is also called perfect substitute, meaning that the firm can perfectly substitute between labor and capital, right? So when those two are equally productive in a marginal sense, then the firm doesn't really make a difference. It's actually how much the firm chooses between labor and capital. So here we are going to do the cost minimization problem when we have a perfect complement production function. And I'm going to make a comparison with our consumer theory again, because there is another important difference in this case. So let me. So similarly, I'm going to use the red color to represent what is fixed. So our budget constraint is fixed in our utility maximization problem. And we can draw a bunch of indifference curves. And to do that, let me first draw this straight line going through all the corners of our indifference curves. we have U equals to U1, and U equals to U2, we have U equals to U3. And we have our budget line that is here, that is fixed. And we know that this point A, is our utility maximization point. Now, in the cost minimization problem, we have so let me see. All right, I'm going to use this red color actually. So we have an isoquant that is fixed at this point. And we can draw a whole bunch of isocost lines. For some given W and R, the price ratio. All right, we have different total cost or iso cost lines associated with different total cost. I probably shouldn't have labeled it over here because it might confuse you. It is not the intercept. It is the TC1 is not the intercept of it. It is what this line is representing. So similarly, this point A, is going to minimize cost, right? Because we must choose a point that is on the isoquant. So if we say choose this point, well, we are going to produce Q0 as we desired, but this is going to incur TC3, and that is going to be higher than TC2. And same as this point, and it is going to be even more costly if we choose point D over here. So point B and point C are going to incur TC3 that is higher than TC2. Point D is going to be even worse. And we can see that point A is the one that incurs the smallest amount of total cost. However, there is a major difference between the cost minimization problem and the utility maximization problem. So now let's suppose the price changes. So suppose there is a price change. And by a price change, we mean that Px increases, or in the producer theory, W increases. And when Px increases, this will make the budget line steeper. And when W increases, this will make the iso cost lines steeper. Now, what will happen to our optimal solution in the two cases? There is going to be a difference. So let's see. If Px increases, the new budget line that I'm going to draw using the pink color, maybe. Oops. So now when px increases, this is our new budget line. It's going to rotate inwards because the price of x becomes more expensive, becomes higher. You can afford less total amount of x even if you spend all your income on good x, right? Now the new optimal point is going to be, let's see, this point. And I'm going to use pink here too. This is our point B, which is the new optimal point. So the optimal point moves from point A to point B, right? When the price of good X increases, you can no longer afford point A. So point A is outside of the new budget constraint, and you will have to choose point B instead. However, in the producer case, when the wage rate for labor increases, let's see what happens. So I'm going to use also a different color, but I'm not going to use pink. I'm going to use this green color. Oops. So when the wage rate increases, I'm still drawing the TC curve for TC1, TC2, TC3, and TC4, all right? And it might look, so I think the color is still fine to make the distinguishment. So actually, maybe I should. So let me use a different color. I think green and blue together are not a good one. So let me use the purple color. Not sure if this is better, but hopefully. So all the purple straight lines are the new isocross lines. They are parallel to each other, but they are steeper than the previous isocross lines, all right? So this is what happens when the wage rate increases. And this is the new TC1, TC2, that is purple, TC3, that is purple, TC4. Now let's see what will happen to the cost minimizing input combinations. So we see that, well, which point will the firm choose? The firm will still choose point A, am I right? So can the firm choose a new point? Let's say that is this point. That is this point, A prime. The firm cannot move from A to A prime, right? Because at point A prime, it is going to still incur a total cost of TC2. So point A prime is going to incur the same amount of total cost after the wage rate increases, as the point A does when the wage rate didn't increase. However, at point A prime, the firm is not producing Q0 units of output. So the firm would still have to choose point A. And effectively, we can draw a new isocost line that is going to be not good. That is going to be something like this. So I apologize if this graph is, I should have drawn this larger. So we can have a new total cost line. Let's call it TC2 prime, for example. And this is going to be between, it's going to be smaller than TC3, and it's going to be larger than TC2. It is this very specific ISO cost line. So now the new optimal input choice is still point A. Only that at point A, the firm is going to incur a slightly different level of total cost. So when there is a price change in W, the optimal input combination, it remains at point A. It does not move like in the consumer's case. It does not change. And the ultimate total cost that the firm has to incur will increase. And in this case, it will increase from TC2 to TC2 prime. So this is an important distinction that in the consumer theory, when there's a price change, the optimal consumption bundle changes, and also the level of utility the consumer realizes. Here we have the level of utility is, at this point, is probably U2 prime, and we know that U2 prime is going to be between U1 and U2. That is at point B. However, in the producer case, when the two goods are perfect complement, the optimal point is going to be always at point A. So I didn't finish this sentence. The TC becomes larger. The optimal input combination is not going to change. It will stay at point A. It's only that with the new slope of the ISO cost lines, and there will be, this point A will be on a different ISO cost line. That is, when the wage increases, it's going to be on a higher ISO cost line. So the total cost will become larger. All right, I think I covered everything I want to say in this. So here, if the firm has a perfectly complement production function, the firm will always choose labor and capital such that AL equals to BK equals to Q0. And this doesn't depend on W and R actually, which is what we concluded from the previous slide. Okay, now let's look at a numerical example. And we have a Cobb-Douglas production function. So let's suppose the production function is Q equals to 2 times L times K. The wage rate is $5 per labor hour, and the capital rent is $10 per machine hour. And the firm wants to produce 400 units of output. We want to find the cost minimizing input combinations, and also the minimized total cost. And here, because the firm can freely choose labor and capital, it is the long run total cost. So to do this, we are going to follow the steps or using the condition that we derived just now. We are going to use the tangency condition. Tangency condition is equating MPL divided by MPK equals to W divided by R. So the MPL is the partial derivative with respect to labor, and in this case, it is 2K. And the MPK is the partial derivative with respect to K, capital, and in this case, it is 2L. and our wage is 5, and our capital rent is 10. So we have this equation. We can rearrange and simplify this equation. So basically we have k divided by L equals to 1 divided by 2, or that L equals to 2k. This is our optimal ratio that we derived from the tangency condition. So we substitute the optimal ratio into our isoquant, which is Q0 equals to 400. So we substitute L equals to 2k into Q equals to Q0, that is 400. This will give us that 2 times L, and L is 2k now. 2 times 2k times k equals to 400. So this is saying 4k squared equals to 400, or that k squared equals to 100, or that k equals to 10. So this is the k star actually that we want to find. And we substitute k star equals to 10 into L equals to 2k. Will let us find that L star is 20. So therefore, L star k star equals to 20, and 10 is the cost minimizing input combination for Q0 equals to 400, of course. We can also calculate the total cost. So the total cost will be W times L star plus R times K star. In this case, it is 5 times 20 plus 10 times 10. And this is 200. So the minimum amount of cost the firm must pay, or the firm must incur, to produce 400 units of output is $200. And let me draw all of those on the graph. And let me put this on the left panel because I'm going to use the right to make a comparison. So let me draw this on the graph. And as always, use the red line to represent the isoquant, or the condition that is fixed. So this is Q equals to 400, the isoquant. And we have our isocost lines that are straight lines. So let me see. This is, so they are somewhat flat actually. Given the wage rate and the capital rent, they are somewhat flat. All right. And this point A is our cost minimizing point, and it corresponds to, so this is L, this is K, and this point A corresponds to 20 units of labor and 10 units of capital. And we can also find that this, because at point A, the firm incurs $200 as a total cost. So this total cost line in the middle is actually TC equals to 200. The other two are sort of drawn randomly. We do not need to figure out what they are, or it's not actually necessary to draw those two. But the ISO cost line passing through point A, we can calculate its level. It is TC equals to 200. And let me move this. So we can draw a graph for this problem. Now, I want to go through another example in the next slide. And I'm not going to clear everything. So let me move this down here. This is what we did previously. Let me erase the graph. And let me solve this new problem. So what is this new problem asking? This new problem is asking that all right, I'm going to solve this new problem on the right. And you can probably see this is regarding return to scale. So now let's suppose that instead of having one large firm producing 400 units of output, what if we have 4 small firms that has the same production function as before, as the large firm we had, Q equals to 2 times L times K, and that each of those 4 small firms produces 100 units of output. What will happen to the cost of minimizing combination the small firms uses? And what is the minimized amount of total cost? So most of the things are going to be really similar, and I'm going to skip some of the steps. So the tangency condition is going to give us the same optimal ratio because we have the same production function. The tangency condition will tell us that L equals to 2K. And if we substitute L equals to 2K into Q equals to 100 this time, it is no longer 400, it is 100. Can I emphasize this? Okay, I can. So actually, yeah, let me use a different color to show it. So this is going to imply 2 times 2K times K equals to 100. That is 4K squared equals to 100. Or that K squared equals to 25. Or that K star equals to 5. So similarly, we can find L star, which will be 2 times K star, and will equal to 10. So for each small firm to produce 100 units of output, going through the same steps we did, well, I mean the very similar steps we did previously, we can find that the cost minimizing input combinations for each of the small firms is 5 units of capital and 10 units of labor. So the total cost for one small firm, is going to be, let's say this is the TC small. This equals to W times L star plus R times K star, and it is 5 times 10 plus 10 times 5, and it is 100 in this case. Now we have 4 small firms, each producing 100 units. So in total, the 4 small firms are producing 400 units, same as the large firm that produces 400 units by itself, right? But what is the total cost or the overall total cost for 4 small firms producing 400 units? Well, then the total cost is 4 times the total cost for each of the small firms. In this case, it is 4 times 100, which is 400. And probably you can see the difference now. Previously, the minimum amount of the cost or the minimized total cost for the large firm, for the single large firm that produces 400 units is only $200. But now, if we have 4 small firms, their overall total cost is $400, which is twice as large as what the large firm would have to incur. So this is what we meant by when we have increasing return to scale. In our case, this production function has increasing return to scale. When we have this feature, one large firm will be more cost efficient than several small firms. All right. So here I chose 4 small firms because the numbers will be integers. You can do the same calculation. If, say, we have 2 small firms, each producing 200 units of output, you can do the calculation. You will find a different overall total cost that is also going to be larger than 200. I can probably put it here, and let me use a different color again. The blue one, maybe. Because the production function exhibits increasing return to scale. One large firm is more cost efficient than several small firms. And we reached this conclusion by solving the 2 different cost minimization problems. We're producing the same quantity of output, same total quantity of output. So I hope this example can feeling what I said previously, that in the last lecture, that the return to scale is going to matter which one is more cost efficient, if it is one single large firm or if it is several small firms. So if you have a production function that exhibits decreasing return to scale, for example, then you will reach the reverse conclusion. You will find that several small firms are going to be more cost efficient in producing the same total quantity of output than a single large firm when the production function exhibits decreasing return to scale. And lastly, if the production function exhibits constant return to scale, and if you solve the 2 problems separately, you will realize that the total cost is always the same, regardless of how many small firms you split the large firms into. So let me highlight what's really important is increasing return to scale over here, so that one large firm is more cost efficient. If you have constant return to scale, the firm size doesn't matter. If you have decreasing return to scale, smaller firms will be more efficient than large firms. So have I missed anything? Right, I think that's what I want to say. All right, now we are going to look at comparative statics. So we have been assuming that the firm produces a fixed level of output Q0, and we can solve the problem. So what happens if we have, if the firm want to produce a higher number of output, what happens if Q0 changes? What does this might look like on the graph? And I'm going to draw one here. And this is the figure 7.8 and 7.9 on a textbook. You can totally refer to those two graphs. Always have labor here, capital here. And so I'm going to use Cobb Douglas as example. So let's say this is the isoquant. And this is, all right, let me draw the first one first. So this is Q equals to Q1, say. And we have some fixed input prices. So we can draw a whole bunch of ISO costs. And I think this one is not good enough. Let me do it again. So we can draw a whole bunch of ISO cost lines. And let me draw another one. All right. And we know that this is our cost minimizing input combination. So point A over here is our optimal point. And this corresponds to the case when Q equals to Q1. Now, if Q increases, so if Q increases from Q1 to Q2, we are going to look at a higher isoquant, right? So a higher isoquant might be something that looks like this. So this is Q equals to Q2, and Q2 is larger than Q1. So the firm expands, the target level of output increases. So based on the arguments we made before, this is going to be the new optimal point, that is point B. And let's suppose the firm increases its output again to another even higher level. So even higher isoquant, which is Q equals to Q3, and that's even higher than Q2. Well, we have a new optimal point that's over here. And let's call this point C. So we can see that as the firm increases its target level of output, the optimal input combination moves from point A to point B to point C. And we can draw a line connecting all those points that might look something like this. And if we extend it beyond, it might look something like this. It's not necessarily a straight line or anything like that's a line, but it's in general a curve. but we can connect all those points and we can draw this curve. So we have a name for this curve. This is the expansion path. So this is the path of the cost minimizing input combinations when a firm expands its total level of output, all right? And however, the expansion paths are not necessarily upward sloping. It is possible that when a firm decides to produce more output, it ends up using, say, less amount of labor. So the expansion path may look different. And on the right-hand side, I'm going to draw another graph. We have labor and capital. We have, and this time let me draw the ISO cost lines first. So we can have a bunch of ISO cost lines. So the isoquant may look like this. It's too bad. Okay, this is fine. So the production function may take a form such that the isoquants look like what I'm drawing right now. It's not okay, those are fine. So in this case, the optimal points are this point, and this point. So this is our optimal point A, this is our optimal point B, and this is our optimal point C. And if we connect those points, so let me move point B here. Here. If we connect those points, the expansion path may be, well, in this case, it is downward sloping. And the optimal amount of labor the firm uses is decreasing as the total output increases, right? So this is the expansion path. This is downward sloping. I want to say that the optimal amount of labor decreases as the total output increases. It's possible. So here we have an upward sloping expansion path. Both the optimal amount of labor and capital increases as the total output increases. So both of these two are possible. And you can see what matters, or what it depends, is the shape of the isoquant. And the shape of the isoquant depends on the production function. So it essentially depends on what type of production function does the firm has. So for the Cobb modulus, I'm going to show you in a few slides that the expansion path is going to be upward sloping. And but possibly for other types of projection functions, the expansion path may be downward sloping. All right, so in addition to what happens when the output level changes, we can also draw a graph to show what happens when the wage rate or the capital rent changes. So I'm also going to draw a graph on this slide. And I'm going to draw labor on the horizontal axis and capital on the vertical axis. And on the second graph that is aligned to the first one, I also have labor on the horizontal axis and I'm going to have wage rate on the vertical axis. So let's see. Let me first draw the isoquant. And a bunch of isocost lines. So actually, let me not draw a bunch of them, but only one of them. That is the maximum one. Let me see. Okay, this is good. So let's say at this blue line, the wage rate equals to W1. So W equals to W1 at the blue line. And the slope of the blue line is negative W1 divided by R. So let's fix the capital rent, but we are going to change the wage rate. And everything will be similar if we change the capital rent, but fix the wage rate. So this is the slope of the blue line. And so given this isoquant and given the wage rate and the capital rent, we can see that this point A, is the optimal point, right? So we can draw a dashed line that's going to go all the way down to the second graph below. All right, so let's say the point that we find over here is L star 1. Well, this looks like L times 1. So let's just call this L1. It is L1 over here. And let's say W1 is at some point. So let's say this is W1. All right, this is the level of W1. So for this value of W1 and holding the target level of output and capital rent R, we solve that the optimal point is point A. And we can draw a point on this graph, on our second graph, which relates W to our the amount of labor that we use. So we can draw a point over here. Now suppose our wage decreases. So suppose W equals to W2, that is smaller than W1. So the slope of the iso cost line becomes negative W2 divided by R, and it is going to become smaller in absolute value, right? Because W2 is smaller than W1. So this is going to become flatter. The iso cost curves will become flatter. We can draw all the iso cost curves we need to draw in the first graph, but I'm going to draw the one that is going to be going to give us the optimal bundle. So when it becomes flatter, it may become something that's like this. So this time, the new optimal consumption bundle is this tendency point, that is point B. And let me also relate this point B to the second graph. And we call this point L2. And we are looking at a new level of W2 that is smaller than W1. So W2 can possibly be somewhere over here. So here I probably want to not use the green color to confuse. Let me use this color. We can plot W2 on this graph as well. And so let me use this brown color over here. This is the point we draw. So at W2, we know that the optimal number of labor the firm is going to choose is L2. So effectively, we can do this exercise for any value of wage rate between W1 and W2, and also above it and below, above W1 and below W2. We can find a trace of the optimal amount of labor the firm will employ, and we can connect all those points on the second graph. So let's say if we connect all those points on the second graph, it looks something like this. It may be a straight line, and it may be a curve, it may be anything, but probably we know that it is going to be downward sloping, right? Because when the labor becomes relatively more expensive, when the wage rate increases, the firm has incentive to substitute labor with capital and hence use less labor. And conversely, when the wage becomes lower, when it becomes less expensive to hire laborers, the firm would want to hire more laborers. So we can derive a curve on the second graph that shows us the relationship between wage rate and the amount of labor the firm would want to hire. So this, in the producer theory, is the input demand curve for labor. It is called the input demand curve for labor. And if you take another course that is labor economics, this is basically our labor demand curve. This is how we derive the labor demand curve. So here we are assuming that the wage rate is exogenous, right? When we solve the firm's problem, we assume the wage rate W is some value that's given to us. And you can imagine we can derive this labor demand curve, and we will solve another problem that will derive the labor supply curve from households. So that will endogenialize. I'm not sure if that's the word. So that will make the determination of wage rate to be endogenous, meaning that it is determined within our model. So we will, the intersection of our labor demand curve and our labor supply curve will determine the market equilibrium wage. So that in that case, the wage rate is no longer exogenously given to us. So we are not covering this in this class. I just want to briefly introduce you to those concepts. And hopefully you will remember if you take labor economics in the future. All right, so this This is somewhat similar to the demand curve we derived in the consumer theory. So in the consumer theory, we derived that what happens when the price of the good changes, what happens to the consumer's optimal consumption bundle of either of the goods. They are very similar in this extent. So here I did a analytical or mathematical derivation of the comparative statics. So instead of putting like numbers into our Cobb-Douglas production function, I can, instead of using numbers, I can use just letters, and I can carry on my analysis. And this might look very complicated in terms of the algebra. You don't have to be worried about it. I will not. I don't want to test you about the algebra, and there is no point remembering the formulas, because only remembering the formulas is, I mean, deriving the formulas and memorizing the formulas is like math, but the reason why we are doing all those steps is economics, and that is what I want you guys to understand and remember, all right? So step 0, we calculate the MPL and MPK, we find the MRTS. Because it's Cobb-Douglas, we can use the tangency condition. We find our optimal ratio, which we can express the amount of capital we use as a function of labor. And it depends on the parameters, W, beta, R, and alpha. That is the equation 1. So we substitute equation 1 into Q equals to Q0, and we just solve it. We express L, the labor that the firm will use, as a function of all the other parameters. So if you look at expression number 2, that's over here. I'm expressing L in terms of all other parameters. And although it looks complicated, everything else is just numbers, right? Q0 is numbers. It is 400 in our previous example. A is also a number. It is 2. It was 2. R is the capital rent. W is wage. Alpha and beta are also the constant numbers given to us. So if you want to verify, you can substitute like Q0 equals to 400, A equals to 2, R equals to 10 or 5, I don't remember, and W equals to either 5 or 10. And also alpha and beta, which are both 1 in our previous example. You can verify that the L star I derived, you will get the same L star. But it doesn't really, it's not necessary to memorize this formula, and it doesn't make any, so I think my point is that I wouldn't want you to memorize this formula. It doesn't make any sense. I mean, it's correct, but it's not really the formula to memorize. I'm only presenting it here to show the comparative statics. And so let's remember, let's look at these two, and I'm going to, in the next slide, I'm also going to have these two equations. So these two are the equations I derived going through all the steps in the previous slide. And I can also calculate the total cost, which is W times L plus R times K. I can substitute into the equation. I can extract all the common factors, and I did all the algebra for you. So here we are ready to talk about some of the comparative statics. So holding everything else constant, what happens if the firm wants to produce more output? That corresponds to the case when Q0 increases. So remember in the graph that we were drawing a few slides ago, the expansion path may be upward sloping or downward sloping, right? Depending on the production function. So here we are looking at a specific type of production function that is Cobb-Douglas. After going through all the algebra, let's see. Now if Q0 increases, which means this term increases and this term increases. And everything here are positive numbers, right? So we can conclude that both our L star, the labor we use, and the capital we use are going to increase. And also because Q0 increases, our total cost is going to increase. So all the other terms that's here are not going to change, but Q0 increases. So we can reach this conclusion for the top dollarless case. Now, when there is technological improvement, which is when A increases, so when A increases, the denominator becomes larger, so the overall that is within the bracket becomes smaller. So we are going to need to employ both less labor and less capital. And also, when A becomes larger, what's in the denominator becomes larger, so the fraction becomes smaller. So we are going to incur a lower amount of total cost, and this is consistent with our intuitions, right? So when the firm wants to produce more, probably they have to employ more labor and more capital and incur more cost. When the technology becomes better, the firm can employ less labor and less capital to produce the same amount of output, and also the firm would incur a lower total cost. Now, what happens when labor becomes more expensive? That is when the wage rate increases. So the wage rate W enters our equation that is in the denominator. So when W becomes larger, what's in the parentheses becomes smaller, what's in the bracket becomes smaller. So overall, our L decreases. However, for capital, when wage becomes larger, what's in the parentheses becomes larger, what's in the bracket becomes larger as well. So K increases. Now the total cost, well, we have our W that increases, we have our L decreases, we have our R that's constant, we have our K that increases. It seems ambiguous whether total cost will become higher or lower, right? But if we look at the expression of it, the only place where W enters it is here. And we can see when W increases, this term will become larger. So the total cost will actually increase. And all the other terms do not involve W in it, right? So although looking from this expression, it is unclear. If we substitute in the actual values of the L and K, we can realize that when wage becomes more expensive, the total cost will increase. And we can also understand this in an intuitive way. So when wage becomes more expensive, firms will have incentive to substitute some labors with capital. That is why L decreases and K increases. And however, the firm cannot perfectly avoid this increase in the labor cost. So the total cost will still increase. Now, lastly, it is quite similar. So if the capital becomes less expensive, that is R decreases, then this is the place when R enters the choice of labor, and when R becomes smaller, L will become smaller. And here, when R becomes smaller, what's in the denominator will become smaller. So what's in the parentheses becomes larger, what's in the bracket becomes larger, and overall, it becomes larger. And it's also intuitive. When the capital becomes less expensive, again, firm want to substitute labor with capital because capital are now less expensive. And lastly, we can see that in the total cost function, this is the only place where R enters our equation. And when R becomes smaller, the total cost will also become smaller. So there is no need that you memorize this expression or derive this expression, but I'm using this to explain those comparative statistics we look at over here. And we can also understand them in a very intuitive manner, as I just explained. All right. All right. So that was a long, but I think quite detailed discussion of the long-run cost minimization problem. Now let's move to the short-run cost minimization problem. So recall the distinction we made at the beginning that in the long run, the firm can freely choose all of its inputs, and in our simplified model, both labor and capital. So here in the short run, the firm will not be able to choose the quantity of capital. And we are going to assume that the capital is fixed at the level of K bar, even if the firm produces 0 units of output. But the firm can choose its quantity of labor. So the firm, in the short-run cost minimization problem, the only difference is that the firm do not choose capital, but can only choose labor. So to define the problem mathematically, we are going to choose labor that minimize our total cost. And the total cost is W times L plus R times K bar, and K bar is going to be given to us. And we are going to also produce Q0 units of output, and the production function is F as a function of L, and F as a function of L and K bar. So here, because we are having this constraint, or because of we have this target level of output, the firm doesn't really have any freedom to choose L in our example. The firm only solves for L such that it can produce Q0 units of output. We are going to see in the next slide what is going on. So same as before, we are drawing a graph. So let me first draw a bunch of isocost lines. And let me draw the isoquant. All right. So this tangency point would be the long run cost minimizing point. So let's call this point A is the long run cost minimizing input combination. It's fine to put it here. Because the firm can freely choose labor and capital, right? So now let's suppose the firm is constrained. So let's say the firm's level of capital, the amount of capital the firm can use is fixed at some point. Let's say this is our K bar. Let's say we have our K bar that is fixed over here in the short run. So this means that, well, the firm can only choose a point on this pink line. However, the first firm must also choose a point that is on the isoquant, right? So this means that the firm is essentially left with no choice but to produce at this point that is over here. So this point B is the intersection of our isoquant and the curve at k equals to k bar. And it is the short run cost minimizing input. So in the short run, the firm will choose point B. So this is this. Now, let's suppose let's look at the expansion path of the firm. So we derived previously, we draw this previously, that in the long run, when the firm is freely to choose different capital and labor with 3 different isoquants, the graph might look something like this. So this is the optimal point. This is the optimal point. So this is the long run expansion path. And let me first use a different color and also move this to a different place. And let me use an arrow to point it to this point. All right, so the orange curve is the long run expansion path. Because the optimal input combinations are along this path as the firm increases its target level of output. Now, for the short run expansion path, we already did that when Q equals to Q0, this point B is the short run optimal point. And we may realize that when we are looking at a different level of target output, the firm similarly do not have the choice to choose capital, but can only find the point where it is the intersection of the isoquant and the horizontal line k equals to k bar, right? So therefore, the short run expansion path is going to be the straight line here, actually, that moves, and let me draw it using a different color. So what? So okay, so hopefully this is helpful. So this is the short run expansion path. It is basically along this horizontal line that k equals to k bar. So we can see the short run expansion path and the long run expansion path are essentially different. And of course, how they look will depend on the isoquant or the production functions. And to find the short run optimal input combinations, we are eventually just looking for the point where the isoquant and the line k equals to k bar intersects. Or to say we solve for labor by substituting K equals to K bar into our production function. So let's go through a numerical example here. So this example, the production function, the input prices are the same as the one we did before. So we have this production function, we have W equals to 5, R equals to 10, and we solved that in the long run, LK equals to 210. And the minimum cost is $200. So now let's suppose that in the short run, capital is fixed at K bar, that is 20 units. What is the short run optimal input combinations? So to do this, we substitute K equals to 20 into our production function, that is Q equals to Q0, and that is 400 units. So this is going to tell us 400 equals to 2L times K, that is K bar, that is 20. And basically we solve for L. What we get is L equals to 10. And this is the L star we are going to use. So the short run total cost is W times L star plus R times K bar. So K bar, it is going to be 5 times 10 plus 10 times 20. So in this case, it is 250. And we realized that this is larger than our long run total cost, which is 200, right? So, and if you were to draw the graph, it is the graph we draw on the previous slide. Now, suppose the short run capital is fixed at a different amount. So instead of K bar equals to 20, K bar equals to 10. Then to find the short run input combination, we substitute K equals to 10 into Q equals to 400. This gives us 2 times L times 10 equals to 400, or that L star equals to 20. Now, in this case, our short run total cost will equal to still W times L star plus R times K bar. It is going to be 5 times 20 plus 10 times 10, 10 times 10. This is 200, which happens to be the same as the long run total cost. And you might have already realized why this is the case, because now the short run capital is fixed at a level that happens to be the same as our long run optimal choice of capital, right? So in this case, the short run optimal combination and the long run optimal combination happens to be the same when the short run capital is fixed at a level that is the same as the long run optimal level. So when the short run K bar is fixed at a level that is the same as the long run optimal level of capital, then the short run optimal point will happen the same as the long run optimal point. All right, so actually solving for the short run cost minimization problem is quite simple. All you need to do is to solve a equation for one variable, labor, because the level at which capital is fixed will be given to you. And we can calculate the corresponding short run total cost and the long run total cost. All right, so this is an extra credit question. So if a firm has a fixed production function, and the firm wants to produce the same level of output, the target level of output in the short run and in the long run. So which one of the following is true? Will the short run total cost always be no larger than the long run total cost? Will the short run total cost always be the same as the long run total cost? Or will the short run total cost always be no smaller than the long run total cost? And I just want to point out that here I'm not assuming any type of the production function. So in general, the production function can be any production function. Or is it that none of the above is correct? That sometimes the short run total cost is larger than the long run total cost, while in some other cases, the short run total cost is smaller than the long run total cost. So you can think about this and provide your answer on iLearn to the week 4 extra credit question. All right, lastly, we want to make a distinguishment between variable cost and fixed cost. So in the long run, because everything is variable, the firm can choose labor and capital, so everything is variable cost. However, in the short run, because the amount of capital is fixed, so the amount of cost that the firm has to pay for that capital is going to be the fixed cost. So among the short run total cost, that is W times L plus R times K bar, the fraction R times K bar, the part R times K bar is our total fixed cost. The part W times L is the total variable cost because should the firm choose to produce 0 units of output, the firm wouldn't have to hire any labor and the firm wouldn't have to incur any of the variable cost. And I believe you have learned the concept of sunk cost in Econ 3. So because the variable cost is, so we are thinking that the firm is making a decision regarding how much output the firm will produce, right? So the variable cost will always be non-sunk because the firm can avoid incurring those variable costs by shutting down or by not producing at all. On the other hand, fixed cost may or may not be sunk cost depending on exactly what type we think. So for example, the fixed cost spent on plant and equipment or land may sometimes be sunk cost. The firm cannot recover those costs, at least not in a short period of time. However, some other fixed costs, such as utilities, may be non-sunk. So imagine that there is a plant and there is a central heating system. And if the firm were to produce, the machines need to operate in a constant temperature and the heating system has to be on, regardless of how many output the firm produces. And however, if the firm decides to completely shut down, then it's okay to turn off the heating system. So this part of the fixed cost is going to be non-sunk. We make this distinguishment, and later on this will be relevant when we want to solve the profit maximization problem of the firm. Let's summarize this chapter. So we distinguish long run and short run. So in the long run, the firm are unconstrained and can freely choose all of its inputs. And in the short run, the firm will be constrained for at least one of its inputs. And in our simplified model, in the long run, the firm can choose both capital and labor. And in the short run, the firm has the amount of capital it uses fixed, but can only choose the amount of labor it uses. We defined the ISO cost lines, which are very similar to the budget lines we saw previously. ISO cost lines are the set of labor and capital combinations that will incur the same amount of cost for the firm. We solved the long-run cost minimization problems. We are essentially looking for an input combination that is both on the target isoquant and also on the leftmost possible ISO cost line. We made comparison under 3 cases, Cobb-Douglas perfect substitute and perfect complement with what we did in the consumer theory. And we can also calculate the long-run total cost as a result of the cost minimizing input combinations. We also solved the short-run cost minimization problem, which is essentially solving for the variable input for the given fixed input. And we can similarly calculate the short-run total cost. And lastly, we defined and compared the variable cost and the fixed cost. We say that variable costs are always non-sunk, while fixed cost may in some cases be sunk cost, and in other cases be non-sunk cost. So this is the end of chapter 7.